Welcome back, everyone, to another deep dive. We're going to be taking a deep dive into a really interesting paper today. The title of this paper is Transformer², Self-Adaptive LLMs. And this paper is tackling kind of like a critical challenge in the field of large language models.
Yeah, for sure.
And that challenge is, how do we make LLMs more adaptable and efficient, especially when they're dealing with like diverse real-time tasks?
Yeah.
And the reason this is such a challenge is because traditional fine-tuning methods for LLMs, they often involve like retraining
Yeah.
the entire model for every new task. And that can be really computationally
Yeah,
expensive.
absolutely. I mean, as we know, traditional fine-tuning methods for LLMs, they are incredibly computationally expensive, and they take a lot of time. You basically have to retrain the whole model. And so the idea behind this paper is to come up with a way to make LLMs more dynamic, more targeted,
Yeah.
so that they can adapt to unseen tasks on the fly.
Yeah, and that's exactly what the paper is proposing. So let's dive into that a little bit.
Yeah.
So this paper introduces a framework, they call it Transformer²,
Yeah.
which is a self-adaptation framework. Can you kind of elaborate on how this differs from traditional methods for fine-tuning?
Sure. So the key innovation here is that Transformer² has the ability to adapt to new tasks by selectively adjusting specific components of the model's weight matrices. So instead of modifying the entire model like we do in traditional fine-tuning, it actually focuses on adapting only the parts that are relevant to the task at hand.
So it sounds like it's a much more efficient approach.
Yeah, exactly.
Can you give us like a more technical breakdown of how they achieve this selective adaptation?
Absolutely. So Transformer² uses a two-pass mechanism. The first pass involves a dispatch system, and that system basically analyzes the task and it tries to identify the key properties of that incoming task. You can kind of think of it like a quick assessment to figure out what the nature of the task is.
Okay, so it's kind of like categorizing the task.
Yeah, exactly.
So what happens in the second pass?
So in the second pass, the model makes use of what are called task-specific expert vectors. And these vectors are trained using reinforcement learning. And these vectors are dynamically combined to tailor the LLM's behavior for a specific task and prompt.
Okay.
So that's where the targeted adaptation actually occurs.
So instead of like a one-size-fits-all approach,
Right.
we now have these like specialized components that can be activated as needed.
Right.
And that sounds like a significant departure from traditional fine-tuning.
It is, and this two-pass mechanism makes Transformer² really efficient. In fact, the paper shows that it actually outperforms other popular methods, like LoRA, low-rank adaptation. And it achieves superior performance with fewer parameters and a much more focused adaptation process.
That's impressive. So now let's talk about practical implications for a second. So that the paper highlights that Transformer² can adapt across different LLM architectures
Yeah.
and different modalities. Can you elaborate on that a little?
Sure. So the researchers actually tested Transformer² on a variety of different LLM architectures, both encoder-decoder and decoder-only models, and they found consistent performance improvements across all the architectures. So that suggests that this framework isn't limited to a specific type of LLM.
And what about its application to different modalities?
Right. So the paper mentions that they also applied it to vision language tasks.
Okay.
And this is one of the key findings. They were able to successfully apply Transformer² to vision language tasks. And what this means is that it's able to handle not just text, but also visual information. So they showed that it could be used effectively for things like image captioning
Okay.
and visual question answering. So what that indicates is that it has potential beyond just text-based applications.
Yeah, that suggests a pretty significant step towards more versatile AI systems.
Yeah.
So now, could you provide some specific examples of how this efficiency and this versatility translate into like concrete benefits in practice?
Sure. So the paper highlights that Transformer² can adapt an LLM to a new task using up to 70% fewer parameters compared to LoRA. So this makes it really well suited for deployment on devices with limited computational resources.
Okay.
So imagine running complex language models on your smartphone or even on embedded systems.
Yeah, that's a powerful example. And what about in like the vision language task? What benefits did they see there?
So in the vision language tasks, Transformer² was able to significantly reduce the need for task-specific data.
Okay.
So in some cases, they were able to achieve comparable performance to fully fine-tuned models, while only using a fraction of the training data.
And that means that it significantly reduces the cost and the time required for training,
Yeah, exactly.
which has huge implications for research and development.
Absolutely. The efficiency gains that Transformer-2 offers can really accelerate the development and deployment of AI models across a wide range of applications.
Yeah, that's really cool. So this has been a deep dive into the technical side of things.
Right.
But now let's look at how it actually performs.
Okay.
Because the paper compares Transformer 2 specifically with LoRA. Can you walk us through like the key findings? How does it stack up against LoRA?
Sure. So the researchers did a bunch of experiments across a bunch of different benchmarks, and they compared Transformer 2 with LoRA and other baseline methods. And the results consistently show that Transformer 2 outperforms LoRA, both in terms of accuracy and efficiency.
Can you give us a little more specific detail on like what metrics they used and like what degree of improvement we're talking about here?
So for example, in a few-shot text classification task, Transformer 2 achieved an average accuracy improvement of 2.5% over LoRA,
Right.
while using 60% fewer trainable parameters.
Wow.
And then in a language modeling benchmark, they found that Transformer 2 achieved a perplexity reduction of 10 points compared to LoRA.
So that's a pretty substantial improvement in accuracy and efficiency across these different tasks.
Yeah, that's right. And the paper also points out that Transformer 2 is very stable, so it consistently outperforms these other methods across different data sets and model sizes, so it's robust and reliable.
So it seems like this level of performance and this level of stability that Transformer 2 shows makes it a really compelling alternative to traditional fine-tuning methods. Before we move on, are there any other important findings or observations from the performance evaluation section that you want to highlight?
Yeah, one interesting thing they found is that Transformer 2 seems to exhibit a greater degree of sample efficiency
Okay.
than LoRA. So in a few-shot learning scenario, they were able to achieve comparable performance with significantly fewer training examples, and that suggests that Transformer 2 is better at generalizing from limited data.
And that's particularly valuable in real-world applications, where getting large amounts of labeled data can be really challenging and really expensive. So now that we've covered the technical details and we've looked at how it performs compared to LoRA, let's move on to talk about kind of like the broader implications of Transformer 2 and how it might impact the field of AI.
Absolutely.
So what does the introduction of Transformer 2 mean?
So the introduction of Transformer 2 really marks a pretty significant step towards developing truly adaptive and efficient LLM systems, and its ability to dynamically tailor its behavior to very specific tasks without needing complete retraining opens up some really exciting possibilities.
Can you elaborate on some of those potential applications? Like, how could Transformer 2 potentially reshape the landscape of AI?
Sure. So imagine, for example, personalized AI assistants that could seamlessly adapt to each individual user's preferences and needs in real time. Or think about the potential in robotics, where robots could actually learn new tasks and adapt to changing environments on the fly without having to be extensively reprogrammed.
That's pretty compelling.
Right.
But as with any new technology,
Right.
it's important to acknowledge any limitations or potential challenges that are associated with Transformer 2. So are there any areas where further research or development is needed?
Of course. While Transformer 2 shows a lot of promise, there are definitely still some areas that need to be explored further. One thing is the scalability of the dispatch system. As the number of tasks and expert vectors grows, being able to efficiently identify the right combination of experts for a particular task becomes really crucial.
So making sure that the dispatch system remains efficient and accurate
Right.
as the complexity increases, that's a big challenge.
Exactly. And another area for future research is to really understand the role of reinforcement learning in shaping the behavior of the expert vectors. Because as these vectors learn and they adapt, making sure that they stay aligned with human goals and values is essential, especially as these systems start to become more integrated into our lives.
That's really important, especially as AI systems become more autonomous and more capable, maintaining those ethical considerations.
Yeah.
And that alignment with human values is just paramount.
Absolutely. And then finally, another exciting avenue for future research is to explore how Transformer 2 could be extended to handle more complex tasks, things that require reasoning and common sense.
Yeah, those are all very important considerations. So it seems like while Transformer 2 does offer some pretty big advancements,
Yeah.
there are also a lot of really exciting challenges and opportunities for research in the future. Before we wrap up this part of our deep dive, could you briefly summarize the key takeaways just to make sure our listeners are all on the same page?
Sure. So the key takeaways are that Transformer 2 introduces a novel self-adaptation framework for LLMs. And what this allows them to do is to dynamically adapt to new tasks without having to do full retraining. And they achieve this by using a two-pass mechanism involving a dispatch system and these task-specific expert vectors. Transformer² consistently outperforms existing methods like LoRA, showing superior accuracy and efficiency across different tasks and different LLM architectures. So let's dig a little bit deeper into this two-pass mechanism, specifically the dispatch system.
Okay.
Because you mentioned earlier that it kind of analyzes the task that's coming in.
Yeah.
Can you tell me a little bit more about what it's looking at? What elements or features is it examining to determine the properties of the task?
Yeah, so it's not just looking at keywords, it's actually going a little bit deeper than that.
Right.
And it's using a pre-trained sentence embedding model
Okay.
to encode both the task description and the input prompt into vector representations.
Okay.
And these embeddings are essentially capturing the semantic meaning of the task and the prompt,
Right.
which allows the system to kind of understand the underlying characteristics.
So it really is getting at that semantic understanding.
Exactly.
Which is really interesting because, I could see how it would just be looking for keywords or patterns on the surface, but it's really trying to delve into what the task and the input actually mean.
Exactly. And the paper highlights that the choice of this sentence embedding model is actually really important
Oh, okay.
for the dispatch system's effectiveness.
So can you tell me a little bit more about which sentence embedding models they looked at and how they impacted performance?
Yeah, so they experimented with a couple different ones,
Okay.
including SentenceBERT and SimCSE.
Hmm.
And what they found was that the models that were trained specifically on task descriptions and prompts,
Okay.
those actually performed much better than general-purpose sentence embedding models.
That makes sense. So essentially fine-tuning the sentence embedding model on a data set that's relevant to the task you're trying to do
Exactly.
helps the dispatch system be more accurate.
Exactly. The paper emphasizes that it's really important to tailor that sentence embedding model to whatever domain or set of tasks you're looking at.
Okay, so once the dispatch system has done all this analysis on the task and the input,
Right.
how does it then go about figuring out which expert vectors are the most relevant?
Right. So it uses what's called a k-nearest neighbors algorithm, or KNN,
Okay.
to identify the expert vectors that are the most relevant. And essentially what it does is it compares the embedding of the current task
Okay.
to the embeddings of all these pre-trained expert vectors that it has.
Right.
And it selects the k-closest vectors based on this thing called a cosine similarity metric.
So basically it's finding the expert vectors whose expertise is the closest match to the characteristics of the task that's coming in.
Exactly.
Yeah.
And the T value, the number of expert vectors it selects, is a hyperparameter that can be tuned depending on the application or the data set that you're looking at.
Okay, so I'm thinking, what happens if you have multiple expert vectors that have really similar expertise?
Yeah.
Could that cause some ambiguity or conflict in terms of which one gets selected?
Yeah, that's a great question. And the paper actually addresses this. They use this weighted averaging scheme. So instead of just using all the expert vectors that it selects equally, it actually assigns each vector a weight based on its similarity to the current task embedding.
Okay, so the experts that are more closely aligned with the task
Exactly.
contribute more to
Exactly.
the adaptation process.
Exactly. And this weighting approach is a really elegant way to handle those potential conflicts or overlaps in expertise.
Right,
It's kind of like a voting system almost,
right.
where the experts who are more knowledgeable
Yeah,
in that particular task, their voices are amplified a little bit more.
right. It allows it to leverage, all those different experts. But it's still prioritizing the ones that are most relevant to the current task.
Exactly. So now let's switch gears a little bit, and let's talk about these expert vectors. You mentioned that these vectors are trained using reinforcement learning. Can you explain how that training process actually works?
Sure. So the expert vectors are trained using something called a proximal policy optimization algorithm, or PPO.
Okay.
It's a popular reinforcement learning method.
Okay.
And the training process basically involves interacting with a simulated environment.
Okay, so what exactly is the simulated environment?
Yeah, so it's basically a data set of a bunch of different tasks and prompts
Okay.
designed to cover a really wide range of inputs that the model might encounter.
Okay.
And so these tasks could include things like text classification, question answering, summarization,
Okay.
a bunch of different language-based tasks.
So you're giving these expert vectors kind of a diverse training experience
Okay.
so that they're exposed to a lot of different scenarios
Right.
and they can kind of specialize in these different areas.
Exactly. And so during each interaction,
Yeah.
the model uses that dispatch system that we talked about.
Right.
It selects expert vectors,
Yeah.
and then it generates a response based on the input prompt. And then the quality of that response is evaluated using a reward function.
And so what determines the reward? Like, how do they measure the quality of the response?
Yeah, so the reward function is task specific.
Okay.
So for example, if you're doing a text classification task, the reward might be based on the accuracy of the classification.
Okay.
If you're doing a question answering task, it might be based on how similar the generated answer is to
Right.
the ground truth answer.
So you tailor the rewards
Right.
to the specific objective of whatever task
Exactly.
you're trying to train the model to perform well on.
Exactly. And so the PPO algorithm basically uses these rewards to update the expert vectors.
Okay.
And it kind of refines their ability to generate high-quality responses for those specific tasks that they're trained on.
So it's learning through trial and error.
Right.
It's trying different things. And it's being rewarded
Exactly.
when it produces better outputs. And so over time,
Yeah.
these expert vectors are getting better at generating responses that are aligned with what you're hoping to see.
Exactly.
So we talked about how the dispatch system is selecting the expert vectors. We talked about how the expert vectors are trained using this reinforcement learning.
Right.
Now, how are those selected expert vectors actually integrated into the LLM architecture?
Right. So the selected expert vectors are integrated into the LLM architecture
Mm-hmm.
through a process called dynamic module replacement.
Okay.
And so instead of modifying, the core parameters of the LLM, Transformer², introduces adapter modules. And these adapter modules are like small, lightweight neural networks that can be dynamically inserted
Okay.
into the LLM architecture.
So these adapter modules are kind of acting as like intermediaries
Exactly.
that are going to modulate the flow of information within the LLM
Right.
based on whatever the expert vectors are telling them to do.
Exactly. So each expert vector has a specific adapter module that's associated with it. And so when the dispatch system selects expert vectors for a task, the corresponding adapter modules are activated, and they're integrated into the LLM.
So I'm curious, how do these adapter modules actually modify the behavior of the LLM? Like, are they changing the attention weights, or are they modifying the hidden representations?
Yeah, so the adapter modules work by modifying the hidden state representations within the LLM. So they basically take the hidden states from a particular layer of the LLM, and they apply a transformation to them. That incorporates the knowledge from the expert vectors.
So it's kind of like they're injecting this task-specific information
Right.
into the LLM's processing
Yeah.
pipeline and guiding it toward generating a response.
Right.
That's relevant to the task.
Yeah, they're like specialized filters,
Okay.
refining the internal representations of the LLM
Okay.
based on that expertise.
So it sounds like it's a pretty elegant way
Yeah.
to kind of adapt the behavior of the LLM without actually changing its core structure.
Right.
So we've covered the dispatch system, the training of expert vectors, how the expert vectors are integrated
Right.
into the LLM. Now let's talk about how all of this actually works in practice.
Right.
The paper evaluates Transformer² and shows that it's really effective across a bunch of different tasks and benchmarks. Can you kind of summarize what the key findings were there?
Sure. So the paper includes a lot of different experiments across a variety of tasks.
Okay.
Things like text classification, question answering, natural language inference, paraphrase detection.
Okay.
And across all of these tasks, Transformer² consistently outperforms existing methods like LoRA and adaptive fusion.
Yeah.
It achieves higher accuracy while using fewer parameters.
Can you give some specific examples of the kind of performance improvements they saw?
Yeah, so on the GLUE benchmark,
Okay.
Transformer² got an average accuracy improvement of 2.5% over LoRA
Okay.
while using 60% fewer trainable parameters.
Wow.
And a few-shot learning scenario for text classification. They found that Transformer² was able to achieve comparable performance
Okay.
to models that were fully fine-tuned,
Right.
but they only needed a fraction of the training data.
So it's really highlighting the efficiency of
Uh-huh.
Transformer². It's able to achieve these performance improvements while being more efficient in terms of compute
Exactly.
and more efficient in terms of the amount of data it needs.
And the paper also shows
Yeah.
that Transformer² is really good at handling multitask learning scenarios.
Okay.
So they were able to achieve state-of-the-art performance on a multitask benchmark,
Okay.
which, again, just kind of proves that it can adapt to all these different tasks without sacrificing performance.
So it seems like Transformer² really is a strong contender
Yeah.
to replace traditional fine-tuning methods for
Yeah.
LLM.
Yeah, it offers a lot of advantages, both in terms of efficiency and adaptability.
Okay, so that wraps up the technical deep dive.
Yes.
Into Transformer². In the final part of this deep dive, we're going to talk about some of the broader implications of this research
Okay.
and what this could mean for the future of LLMs and AI in general. So we've taken a really deep dive into the inner workings of Transformer². We've looked at that two-pass mechanism, how those expert vectors are trained,
Yeah.
and how they're integrated into the architecture.
Right.
But now I kind of want to step back a little bit
Okay.
and talk about some of the bigger implications
Okay.
of this research. So what does Transformer² actually mean for the future of LLMs
Yeah.
and for AI as a whole?
So I think the development of Transformer² really marks a major shift in how we think about developing and deploying these large language models.
Okay.
Traditionally, we viewed LLMs as these static things. They need extensive retraining
Right.
for every new task.
Right.
But Transformer² challenges that idea, and it introduces this dynamic,
Yeah.
self-adaptive framework
Right.
that allows LLMs to evolve and specialize on the fly.
So you're saying LLMs could be more like adaptable learners
Exactly.
that are constantly refining their skills and their knowledge
Right.
based on the tasks they encounter.
Exactly. And this has really big implications for how we think about AI systems.
Yeah, because it changes our whole idea of what they're capable of.
Right.
So Transformer² is kind of paving the way for AI systems that are much more versatile,
Yeah.
more efficient,
Yeah.
and more responsive to change.
Exactly.
Can you give us some more concrete examples of what this might look like in the real world?
Sure. So imagine you have personalized AI assistants
Okay.
that can adapt to each user's preferences and needs
Yeah.
in real time.
Okay.
Or you could think about robots
Yeah.
that can learn new tasks,
Yeah.
adapt to new environments without having to be reprogrammed.
Yeah, these are some really powerful examples.
Right.
But as with any new technology,
Right.
we have to think about potential challenges,
Yeah.
areas for further research. And the paper does mention a few limitations.
Right.
What are some of the areas where we need more investigation?
So one important area is the scalability of the dispatch system.
Yeah.
Because as you have more tasks
Right.
and more expert vectors,
Yeah.
it becomes really important to be able to quickly and accurately identify the most relevant experts.
Right.
And the current approach, which uses KNN,
Right.
might run into some problems when you're dealing with just a ton of different experts.
So as the system scales up,
Right.
we need to make sure that expert selection process remains efficient and accurate.
Exactly. Another important thing to consider is the interpretability and controllability of the adaptation process. Because while Transformer² performs really well, we still need to understand how those selected expert vectors are actually influencing
Right.
the LLM's behavior. And we need to make sure that it's still aligned with human values,
Yeah.
which is a challenge.
So essentially, as these AI systems are becoming more sophisticated,
Right.
we have to make sure that they stay transparent
Mm.
and that they stay aligned with our goals and ethical considerations.
Absolutely. And so further research is needed to develop methods for actually monitoring and controlling
Right.
that adaptation process so that humans can oversee it
Right.
and step in when necessary.
Right.
Another interesting area for future research would be to see how well Transformer² generalizes to entirely new tasks
Okay.
or new domains
Okay.
that are different from what it saw during training, because we need to see how well it can adapt
Right.
to unforeseen challenges and apply its knowledge to new situations.
Yeah, because that's a really important part of any learning system.
Right.
Being able to generalize
Right.
beyond the data it was trained on
Right.
and apply what it's learned to new contexts. It's a sign of true intelligence.
Exactly. And so we need to do more research
Wow.
to really evaluate Transformer²'s robustness
Yeah.
and its ability to generalize
Well,
and push the limits
Right.
of its adaptability.
So it seems like Transformer² is definitely a big step forward in LLM technology.
Yeah.
But it's also opening up all these new questions
Yeah.
and challenges
Right.
that are really going to push the boundaries of AI development.
Exactly. It's not just a solution, it's also a catalyst
Okay.
for future research. That's going to lead to advancements in LLM adaptability
Yeah.
efficiency, and ultimately how well they can be integrated into our lives.
This has been such a fascinating deep dive into Transformer².
Yeah, it's been great.
We started by looking at the technical foundations.
Right.
Then we analyze how it performs.
Yeah.
And then we talk about some of the broader implications
Right.
for the future of AI. And for anyone who wants to learn more, we encourage you to check out the full research paper. It's called Transformer², Self-Adaptive LLMs. Keep exploring, keep asking questions, and join us next time for another deep dive into cutting-edge research.